Okay, hello. Today we will continue with secure computation. Let me see if I have a good picture to flash back some reminders from some reminders of where we were last time. Hold on. No. Okay, here I have the notes. Hold on a second. Okay, so we did the GMW construction, Goldreich, Michalik, Whitgerson, that used Boolean circuit and OT to do a secure computation of the Boolean circuit in a two-party setting. So you represent computation as a Boolean circuit, inputs of P1, inputs of P2, and for now we continue focusing on a two-player case. Each of these protocols that we describe will, each of them does have an extension to a multi-party, but some have an easier extension than others. And also we'll talk soon an extension to general access, to a threshold access structure. So we would like to handle any T out of N malicious participants. Yeah, so the best, it seems that N-1 cheaters is the best threshold to go for. Yes, because if you can withstand N-1 cheaters, then why wouldn't you? But a computation where any N-1 people cannot compute on their own also has the property that if you lose just one player, then you cannot reconstruct the inputs, and so the computation is not robust. It cannot output anything. Of course, if they notice that one party is misbehaving, they can just restart the computation on their initial inputs, but that doesn't work in all applications. So that would be also a concern, but not for now. Okay, so we represent the computation using Boolean circuit, and we compute gate by gate. So we have the following phases in the GMW construction, but these phases will also well, they will be similar in many multi-party computation aspects, although today it's not really broken into the. So each in the secure computation I'm going to tell you about today, these phases are not so pronounced. But in GMW and many others, in a phase one, you commit your every party commits their inputs by secret sharing them in the two-party case between P1 and P2. So each of the input wires are secret shared. This is the beginning. Then the protocol computes gate by gate from shares of the input to shares of the output of the gate. And if we have that block of computation, then we can repeat it for every gate in the circuit until we get to the output. And then we just need to reconstruct the output. So the secret sharing we saw last time was the XOR sharing. You share any value, any input of X by creating two shares, one for P1, which is P1 would hold that share for himself, the other would send to P2, such that one of these shares is picked uniformly at random, and the other is the XOR of that one and the value. So secrecy follows from a one-time pad argument. Okay, and you can at least you can see that okay, it's not hard to generalize this sharing to n party case, right? If P1 wants to share his inputs among n parties, he can compute n such shares, n minus one of them completely random. The nth one is an XOR of the n minus one shares and the value. And again, this one-time pad argument will show that any n minus one of such shares are uniformly distributed n minus one random strings. Okay, in this case, all these inputs are bits, so these things are just bits. Okay, and the inner protocol was an OT, right? And there was this very cute, clever way of mapping between gates of the computation and instantiating the gate computation from shared input X and a shared input Y as a kind of two-party distributed lookup into this table, right? We one of the parties, this was an asymmetric protocol. We treated one of the party as a manager, so to speak, of this lookup table, because thankfully, the lookup table in some sense is public, right? Because these are Boolean gates that everybody knows which gate we're computing and whether it's an AND gate or a NOR gate or a NAND gate or whatnot, right? So this table is defined. And so one party, the manager, so to speak, which was P2 here, creates a shifted lookup table, shifted by the P2's shares of X and the P2's share of Y. And P1 uses its shares as the index to the lookup, to this table. And thanks to the OT, we have a way of one party has an index, the other a table. The guy with an index gets the value that is indexed by his inputs, while P2 learns nothing, right? All right. Okay, so that was the GMW. What is now we are going to this was actually before GMW, shortly before. It is Andrew Howe's Garbled circuit construction from 86 for protocol for multi-party computation. In again, the setting is we have only two players, and we tolerate either one of them being faulty. I mean, being an attacker who tries to learn the inputs of the counterparty. It's exactly the same setting as we have just seen in that version of GMW. Although, yeah, we skipped for now how GMW extends to n players. But you know what? Maybe it's really well. How would it extend to n players? Okay, so you have the sharing, as we said, it's easy, right? There's n parties holding these n-1 shares. Let's say we try to do this, right? What changes? Well, again, there is a gate exactly like this, and one party could implement a lookup table. The thing is that the index into this lookup table is shared now between n-1 players. If you just take the shares of n-1 shares, right? Like if you extend the sharing to n parties, fix one of them, make one of them this lookup table manager. There is n-1 left. If you took these n-1 shares and collapsed them, I mean XOR them all, you would have exactly this situation, right? Because the XORs of n-1 would form this sharing. So the XORs of the n-1 holders of shares for X and Y, if you XOR their shares, you would form this index, the lookup index. So what you need is an OT where the index is not held by a single party, but by n-1 parties, and it's secret shared. Okay, and okay, this is not the end, because this guy now has to actually, that's not enough, because that would be that this guy creates basically shares for everyone, and now the manager, basically each of them is going to create their share. Okay, but this guy would know all of them, right? So well, okay, so that's the puzzle. That's where the extension is going to, but it's not such a hard extension. So this is something that you can try to solve, okay, as an exercise. Like, how would you upgrade this to the setting where these indices are secret shared, and you have this OT tool, okay? Okay. So still, but the version we saw is still in this setting. And again, as for the versions we saw, the other sort of salient question that we kept without addressing is, this is only for honest but curious. So honest but curious, meaning i.e. all follow protocol. And let me stress that the issue of all parties following the protocol is not just an issue of whether this computation will create a sensible output, right? Because if a party misbehaves, they can probably steer the computation to create some crazy outputs that perhaps is irrelevant. There is two questions, at least, that are apart from, that are separate from, is the output, if you have a malicious party who is spying, as in the solution, but also diverges from the protocol, is the worst thing that they can do that the outputs are useless, or perhaps the computation just terminates with some fault? Well, not necessarily. First of all, first of all, if P1 computes some output that is incorrect, so at some point during this computation, perhaps P2 always consistently plays this OT manager role. And for example, he populates these lookup tables with arbitrary values of his choice. Clearly, he can basically compute different Boolean gates, right? Because the manager is trusted to embed into these values, to create these values correctly based on the Boolean gate. Now, if he is malicious, he clearly can not do that, right? And in the very least, he can embed these values for a gate of his choice, his or her choice, right? Now, what does that mean? That means that basically, whereas P1 thinks that what they compute is this circuit, malicious P2 rewrites the gates in an arbitrary way. They have to keep the topology because P1 is going to expect that the computation, has the follow, 5 gates in the first row that are wired certain way, then 10 gates in the next depth of the circuit wired in some fixed way. So the wiring of the circuit is fixed. P1 will, expect certain wiring, right? Will input his inputs and treat them as so. That's kind of fixed even for a malicious P2, but P2 can rewrite the gates. So since they create the output, remember this trick. How did we hide? Why could we reconstruct this sharing at all? Because this sharing was supposed to encode both P1's output and P2's output. How? XORed using part of the input was a random pad, right? So P1 was contributing a random pad, and some of these gates towards the end were supposed to XOR the real output with the one-time pad. Okay, how about P2 just compute the whole thing correctly and then mess on this final output so that to make the gates that are supposed to XOR with the one-time pad of X, make them just identity. Just ignore this one-time pad and just a copy of the output. So make this stuff encode the true output of P1. Okay, and basically everything is broken, right? I mean, actually you can cheat even better. If the circuitry of this, if the wiring, why don't you make these gates basically identities on X1 inputs, so that X1 input is going to be revealed in the output? Well, that's the most damaging things that P2 can do, right? Like he just learns the input from the of course, well, you're going to say, okay, how can I deal with these cheaters? Perhaps I redesigned the circuit so that this is impossible. But that's hard, right? We want being able to compute for arbitrary circuits, and now security is dependent on what circuit we're computing. And a second and a more subtle way for P2 to cheat is that so not only he can reveal more information about X than designed by the circuit, right? By cheating on the gates. He can also make P1 output stuff that is basically not based on this. So for example, think of this circuit as implementing an equality function. So this is a password authentication. P1 X is P1's password. Y is P2's password. The circuit just checks their equality and tells P1, perhaps privately, XORed by some of this one-time pad, a decision value, which is Y equal to X or not? Well, P2, if he's the OT manager, he can cheat on that gate and just fix it to always output 1. Yes. So steering the output of P1 or revealing more about the input of P1 than is allowed by in the ideal setting, right? Which we want to emulate, which was that that only the function outputs are leaked, right? Both of them can be violated. Okay. how to upgrade these protocols to a malicious attackers, we leave this for now. Okay, the same for YAOS protocol for at first. Okay, but however, so this is just like GMW, and that one was, I think, 87, except extension to GN being any setting like this is possible but harder. But basically less efficient as a okay than what we said about the GMW. And okay, the protocol, but and this is the big advantage, YAOS protocol is constant round, while the GMW took order of depth of the circuit runs, right? Because for every level of the circuit, we could parallelize the OTs, but we didn't know how to do it faster, right? Each level of the circuit requires a round of OTs. And YAO shows you can actually do it differently in constant rounds. But the bandwidth of YAOS protocol is the order of the size of the circuit times the security parameter. So this is the size of the circuit is the number of gates. For every gate, we need to send basically cryptographic keys, whereas in GMW, the bandwidth was just the size of the circuit. Okay. Plus a poly of SecPar. So now in the GMW I showed you, for every gate I needed OTs. So for every gate I pay the price of an OT. So the basic GMW, okay, if it's so this is the bandwidth, because at every gate I need an OT. And how did I implement OT? If OT is if each OT is implemented independently. Right? Because the bandwidth of OT is order of security parameter. Why I need? What did I show you about OT? I need a group with the DDH assumption. This could be an elliptic curve where the group size is linear in the security parameter. So, like 256 bits per each ciphertext, right? And how could you implement OT? It was an encryption of the bit and an encryption of the two messages, but each of them is a group element, right? So a constant number of group elements per every gate. That's the same, roughly, right? Same order, but it goes down. But it also but it also can be done in this with this asymptotic bandwidth, where if the circuit is large, then this term vanishes and this term is dominant, and you are hugely different, right? Now, how big is this constant here? It could be like 3 bits per gate. I think that's the best result. How? If all OTs implemented with so-called OT extension. Okay, so with the OT extension. Okay, so to be seen. Okay, right? Like we will have to come back and see how these OT extensions work, so that the price you pay some price related to security parameter to initialize, but after that you can perform OTs at the bandwidth, first of all at the cost of just symmetric crypto, and also at the bandwidth that is related to how big are the messages that you're transferring. These are the messages that you're transferring in OT, and in the case of GMW, these messages are bits. This is bits. These are bits. All of these are just bits. So that's why it's a constant. It's a constant bandwidth per an OT instance. Okay. Okay. So there is a trade-off between computation that can be done in low round complexity, but it has a larger bandwidth. Or you allow computation to go for more rounds, but you win on bandwidth complexity, right? So which of these tools? Okay, well, perhaps we can improve some of them, right? So the game is not over by any means, but for now in implementations, you see, well, if you have low bandwidth, even though you have more rounds of computation, if you can pipeline your application, right? If what you compute is pipelined, then the total throughput is going to be dependent on the bandwidth, but you have larger delay in computation, right? Because caused by the round complexity in GMW. Yes, so the computation has a different form. Higher throughput, longer delay compared to Yar's garbled circuits. Okay, and so it can, it's dependent on the context which one is going to be better. Okay, let's see. Okay, so Yao's garbled circuit construction. Again, we have the same setting of two players having binary inputs, and the computation is formed as a circuit. We have circuit okay, and what I and just like GMW, it's also designed so we have the same threshold, the same adversarial setting, and also the same representation of the functions that we compute designed for Boolean circuits, right? So we again represent the functions that we compute as a Boolean circuit, right? So it has some gates, etc. They are wired somehow, and yes, and perhaps like so. Etc. Right? And somewhere we have the final layer of the circuitry that outputs the final outputs, and we reconstruct these final outputs to both players. Okay. So now even in a GMW case, the initial sharing was symmetric, and the reconstruction was symmetric. Computation of each gate was asymmetric. One player played this OT sender, the other OT receiver. By the way, they could switch at every, for every gate, they could play independent roles, right? So it's all right. But here, the protocol will be even more asymmetric. So you could see for function f that takes a pair of inputs and give an output C. And let's assume inputs are n bits and outputs are n bits. It is not necessary. The output input of both parties can differ in length, and you don't have to pad them to equal length. Okay, so P2 will garble circuit C. What is garbling? So a garbled scheme is a well, it's a pair of I can say garble and eval algorithms. The algorithm garble outputs two things. Garble takes a circuit, and it's a randomized algorithm, and it creates two things. The garbled, well, I can denote it like this. This is the garbled circuit C, okay? And a set of garbled inputs. Let me think quickly. If I want to switch a notation, yes, I think I do. So this is X garbled. X you know what? It's okay. I can continue with this notation. So X I B for I 1 2. So let this stand for a set of indices from 1 to n. Okay. So B is a bit, and I is an index like this. And I also am going to create garblings of inputs that corresponds to my own inputs. So P2 will perform this garbling. From P2's perspective, Y's are her inputs, X's are the counterparties inputs. So P2 will garble inputs of the okay. Just a second. Let's okay. This is the outputs of garbling. What are these things? These are garbled inputs. Garbled, I can call them keys. Okay, and there is a garble. So basically, from when you garble, it doesn't matter whether some input wires are your own or some input wires are the counterparty's inputs. You really treat them all equal. These are all the input wires, right? And you, for every input wire, you create two values, one corresponding to, you can call it a key, one corresponding to the value on that wire that corresponds to bit 0, and the other key value of that wire, that the 1-bit value of that wire. Okay, so far I didn't tell you what to do with this stuff, right? So there's no such a clear semantics to these outputs of a garble. So that's going to be clear in eval. Eval, when okay. Eval, given the garbled circuit and a vector of values x hat I yes, hold on. You know what? Let me do a different notation. Let me do a different notation because this is just going to kill me. Okay, sorry about this. um, um, so P2 garbles circuit C. Garbling scheme is a pair of algorithms, garble and eval. And here we'll during garbling, okay, assume the following notation. Assume C computes on input just X and outputs Z, okay? And assume X has length N and length of Z does not matter. So we rename X, Y as X, okay? It's just because for garbling's perspective, it doesn't matter which wires belong to P1 and which wires belong to P2. Let's just call all the inputs X. Okay. Okay. And now with that notation, is going to be easier to write. That the garbling of the circuit is a randomized procedure that creates a garbled circuit and a set of keys that I is in for every input wire to the circuit. I create two keys, one for bit 0, one for bit 1. Okay, so these are the two outputs of the garbling, and eval on inputs in the garbled circuit, and an input, the set of keys whose there is one key for every wire, okay, for every input wire. But which key? Well, designed by the bit of the input X, okay. If the evaluator gets the garbled circuit and gets these keys for one key for every input wire, and which key? Well, as determined by the bit of the input X, then what they can evaluate the output is the value of the function, the circuit applied to input X. Okay, these are the two, well, these are syntactic, what these produce. And for completeness, completeness is that if C and the set of Ki are output by the garbling, yes, garbling of circuit C, okay, then for all input X, which are n bits, eval applied to the garbled circuit and the set of keys which are indexed by the proper bit of input X, outputs is going to output the value of the circuit evaluated at X. Okay. Okay, that's completeness. What are the secrecy properties? So security properties of garbling. Well, first of all, if you C hat, well, let me think. Well, so here's the security property. For every possible input X, a C hat and the set of keys that corresponds to that input X leak only C of X. In other words, so well, eval, you can apply the eval procedure to the Garbled circuit. Circuit is public, right? This whole circuit is public, right? Public circuit. So everybody knows what the circuitry is and what all the gates are, because both P1 and P2 engage in this computation with a knowledge of what it is, what function are they computing, right? Password authentication, set intersection, some database mining algorithm, what have you. They will engage in it and allow one another to compute the output. Only knowing what it is that because they agreed, they know what they're computing, right? So the circuit is not hidden. What the purpose of secrecy is hiding the inputs bits. If I reveal the keys, so when I garble, I create these keys for every bit. If I reveal the keys, the set of keys that correspond to some choice of input bits, then by the completeness of eval, I will leak this output of the circuit on these inputs, right? On that input. But will I allow somebody to compute the value of the circuit on some other X? For example, X, but with one bit flipped, okay? Or any other function of X. Look, adversary, he knows C, so he can compute C on arbitrary inputs. The question here is that there is some particular inputs of P1 and P2, and those we want to protect. We were asking, what is this whole computation going to reveal about that particular input? Let's rename that whole input string X. We will perform, well, cutting down to a chase, one of these parties, let's say P2, will create this garbling, and the garbled circuit will be known to both. And the keys that correspond to the input bits will be revealed to both. So both of them will be able to do this evaluation procedure and compute the output. The question is, what else is leaked about the bit, the input vector X, by the presence of this garbled circuit and these key bits? And the security property is really one, okay, that it leaks nothing but this. How are we going to frame it? In the standard way, i.e., there exists an efficient simulator algorithm sim such that for every x, sim who is given just the y which is equal to c of x, sorry, I call it z, who is given just the input, the output, sorry, just the output of the circuit on input x. From that output, you can simulate the Garbled circuit and the set of some keys like this, which are indistinguishable from C and KIXI that are output by Garbled. By Garbled and X, right? So how are we? What are we comparing the view of the simulator with? You're comparing the view of the simulator. Well, what is the simulator's output? We want the simulator to output this tuple. I mean, we want the simulator outputs to be indistinguishable from this tuple, right? So this is the simulator's output, and this is the tuple. The tuple is, sorry, the Garbled circuit, and those keys from the set of the wire keys, input wire keys, that are designated, that are indexed by the bits of X. So every choice of X, right, determines this set. Okay, there's two things that determine this set. First of all, the garbling procedure determines the keys, the whole set of keys, and then the choice of X determines the particular keys that are revealed in this view. And a garbling scheme is secure if there is an efficient simulator that can create something that looks like a garbled circuit and something that looks like these n keys corresponding to input X, but the simulator does it without knowing X. The simulator does it using just the output Z. Okay, so that's a garbling scheme. Now, how are we going to use it? Yao's. So first, let's see how Yao's protocol, Yao's construction using garbling, and second, of course, we have to say how do you get such a garbling scheme, right? So P1 has this input X, and P2 has input Y. Okay, and what P2 does is the following. First of all, so first P2 runs the garbling algorithm to create the garbled circuit, and the keys corresponding to every possible bit on an input wire. But now I want to go back to this setting. Okay, so so my notation will be that first n wires, n input wires are for P1's input X, and last n input wires are for P2's input Y. Okay, so from the point of view of garbling, I collected input X and Y and treated the circuit as if it has some n inputs, and created keys, both a 0 key and a 1 key for each input wire. But now I need to be cognizant of the fact that some of these inputs are belonging to P1 and some to P2. So I need to create, I have 2n total input wires. Okay. First of all, P2 just sends the garbled circuit to P1. And for his input wires, he so the following, this is not clear from this property, but it's a consequence of this property, that if for any circuit you have a simulator that can create these keys just from the output, okay, I mean, he doesn't create these keys, he creates keys that look just like the real keys output by a garble that correspond to some input vector X. Then in particular, it must be the case that if the keys by themselves do not leak whether a given key does not leak which of these bits he's for, okay? Because if the simulator can do it, let's say that these keys, just from the keys, you can tell what is the bit Xi. So in the real view, given the keys, you would be able to tell, oh, okay, this is the key for bits X1 equal to 0. And the following key is the key for X2 equal to 1. Then if that was really visible, then a simulator would have to match that view, right? And the keys that simulator produces would have to encode input X in a visible way. But how can it be? Simulator does not get X. Some circuits, the output is enough to compute the input, right? There's some trivial circuits, like an identity, okay? Where given the input, output, you immediately get the input, but not true in general. So therefore, the simulation really implies that these keys are input hiding. So if you reveal the key, you cannot tell whether this key corresponds to a 0 bit or a 1 bit. And so what P2 will do for, he will send his input, the keys correspond to his input bits, which I guess I can index like this. Okay, so it's a key on a wire n plus I, because the first n are for P1, the last n are for P2, so they go from n plus first, n plus second, all the way to 2n. And which of the two keys he should give? This one. So for a wire indexed n plus I, P2 reveals k n plus I indexed by bit B, where this bit is equal to the ith bit in his index. Okay. What we want to Okay. Let's say that we only care about P1 computing the value C of x. Well, P1 is almost there. He has the garbled circuit, and he has the keys that correspond to all P2's input wires. And the keys that he got on those wires correspond to P2's input bits. Okay, so it's almost like here. What is he's missing? He's missing the same set of keys, but corresponding to P1's input. But that's an OT. So, so we're running the following box for all I1 to n. This box, what a P1 contributes to it is xi, is the choice, is his bit on the ith wire. What P2 contributes to it is two values, x, key k corresponding to wire I, but for the bit 0, and a key ki corresponding to wire y, but the one of two keys created for that wire, right? One key was created for that wire with the intended bit 0. This key corresponds to the input bit on that wire being equal to 0. And this key corresponds to the input bit on that wire equal to 1. Since the bit on that wire is xi, and xi is the choice bit in OT, what this OT will output for P1 is precisely what he needs, which is the ith wire key, but which indexed by xi. And this is repeated in parallel, right, for all n. And OT, the ones we have seen, right, like they are secure in parallel. So at this point, so now the P1 is going to run the garbled circuit evaluation using the garbled circuit, and the set of keys, basically the union of this set of keys, right? So he will use the KIs that are output of the OT. So assuming everybody was honest with the protocol, what he will reconstruct is the keys for from 1 to n, right? The keys on the first n inputs that corresponds to P1's input bits, and you know, concatenate this vector with the vector of keys that corresponded to the P2's input wires, indexed by the bits of that P2 contributed, and this again, it's in this set, right? Okay, and by the correctness of completeness of evaluation procedure, a Garbled and evaluation, this Z is an output of C on X concatenated with Y, right? So this is the vector of 2n bits. Yeah. that the bits are half of them controlled by P1, half of them controlled by P2. And then finally, because we are in the honest but curious model, then P1 can just send those in outputs to P2. Right? Security for what does P2 learn about X in this protocol? He learns nothing here, because so by security of OT, he learns nothing about these choice bits. He learns nothing here, clearly, right? He just sends stuff out. And the only thing he gets back is the output. So for honest but curious P2, who garbles correctly and participates in OT correctly, he gets exactly the output of the circuit only. Of course, just like in the GMW, you have to ask, okay, but what about the dishonest P2? Can he not control the way this is done? Can he not control the way this is done so that to get much more about X input in Z than was intended? And yes, this will be true. So we'll look later about ideas for how to force honest behavior from P2 effect, or tolerate any divergence and still show that whatever divergence happens will either be caught and P1 will terminate and not send anything, or whatever it sends is leaks out only, can be simulated from the outputs of the circuit. Now, what about P1? What did he learn? Okay, well, he just really learned the stuff and this stuff. So the inputs that he gets here are the only things he learns, right? By OT security, he learns only the bits corresponding to Xi, and this is by, so what he learns is exactly a solution like this, a garbled circuit, and the keys that correspond to some choice of the bits that were jointly determined by X, some of them, right? Some of these wires here are determined by P1 and some by P2, but that view can be simulated from an output of the circuit, which is supposed to be revealed in the secure computation, right? So you get a security for both parties follow from security of OT and from a security of a garbling scheme. The fact that this is round complexity is constant is okay, it's right here. And now let's see, how do you garble? Okay. Oh, sorry, I guess, I didn't look at this screen, so I hope this was visible when I was talking about it. Okay. So, how do you garble? There is, I'll show the original garbling by Yao. And there is many improvements done for it since, including some really surprising ones. But let's see the basic construction. So the garble, Yao's garbling scheme, many improvements since. Assume C was going from X to C such that both inputs and output have length n. These are not necessary assumptions, okay? It's just for simplicity of notation. You can see, for example, here, right, we have the simplifying assumptions that P1 and P2 have the same number of, the inputs are as same length. Does anything get more complicated if they have different lengths? You know, if there's only 10 bits here and 1,000,000 bits here? No. You know, there's just 1,000,000 bits sent over here, and there's 10 of these OTs. Okay, there's you know, stuff just adjust in a very natural and simple way. So likewise, the garbling is just a notation simplification. Okay, so let the circuit be as a set of set G of gates and set W of wires, and there is a map from a set of gates to the set of wires, where these are the left and right inputs set of a gate, and this is the output wire of a gate, right? So you just indexed wires and you index gates, and you have a map that tells you, you know, which two wires are the input wires for certain gates, and which wire is the output wire of a certain gate. Okay. So now Garbled is going to do the following. For each wire W, pick two keys, KW0 and KW1, both random from as big as, well, from they're random keys. Okay, the length is the security parameter. Already this let I be the it's a subset of W, which are the input wires, and let O, which is a subset of the W, be the output wires. Okay. What do we need from a garbling scheme? We need to create a garbled circuit and a set of garbled wires. We already have the set of garbled, the garbled keys. We already have that set. K so this defines a set KWB for every bit, and every W, which is in a set of input wires. Okay, so I call them, I just index them from 1 to n in this notation. Now I index them as whatever indices W's these were, but they belong to the set of input wires I, capital I, right? So it's just a notation, right? If you were just input wires were wires number 1 to n. Here is arbitrary wires can be called input wires, right? But that's a small notational difference, right? Okay. So we have the wires, the keys corresponding to input wires. What is the garbled circuit? For every gate G in the gate, let L, R, and O be respectively left input, right input, and output wire of gate G. Okay, so so you have a gate. This is my gate G. It has an input wire that I'm going to index L. Input wire I'm going to call R, and an output I'm going to you know what? No, let me change this. I'm going to rename them X, Y, and Z. Okay, these are not the total inputs of the circuit and the total output of the circuit. These are indexes of the wire. No, oh my goodness, I'm sorry, that's a bad choice. Yeah, let's go back to left, right, and 0 and O. So this is the left, this is the right, and this is the output. These are just indexes. So L, R, and O are indexes of wires. Okay, so there are elements of W. They're not the bits, the input and the output bits themselves. So in plain text computation, this would correspond to having some bit. So let XW stand for bit on wire W in a computation. So X I for I in I are inputs to C, and XI in I in O are outputs of C. Okay. Okay. So in the plain text computation, I will have some bit called XL on this wire, a bit called XR on this wire, and I will be computing gate G on these two, and XO would be the output bit. As before, right, I have this gate is public. All the gates are public. So XO is a function of XL and XR, which can be written like this, where this vector, right, is the determined by gate B, by gate G. In a garbled computation, in a garbled circuit, I want to replace this system where I have bits as input and I have a known gate and I just do a lookup and I know what the bit on the output wire is, and so I compute. In a garbled circuit computation, I will have a key corresponding to a wire L, and there's two such keys. One corresponding to a 0-bit input, a 0 value on that wire, and one corresponding to a 1-bit value on that wire. Which key I will have? It will be determined by this bit. So in the initial computation, for all the input wires, which bits did I start with? I had KIs for the input wires, right? So let's say this is the one of the input wires. So it's from 1 to 2n. And which of the KI I had? The one that corresponds to the real bit input on that wire. So, for example, for P1s, if that wire corresponds to P1's inputs, the bit that told me which of these two keys, KI0 or KI1 I had, is determined by the bit on that input on that wire. Yes, so this is the initial setting, and I will have that as an invariant throughout the computation. The value on the right will be the key corresponding to that wire, and which one? This one. Okay. What I will have here is not the gate, but the garbling of the gate. And what I want the garbling to give is the key on the output wire. Which one? Well, the one that corresponds to the value of that gate at the proper index. And which index is the proper one? The one determined by these bits. So the index here is, you know what? Let me change the notation. So this is not subscripts, but it's a functional notation. So this row is a G of 0, 0, and this row is a G of 0, 1. So this will be a G of XL XR. The garbled circuit will be, let's say that I had a representation of this garbled gate, which allowed computation of this key given any 4-tuple of possible inputs here. Look, there is 2 possible values on this wire. There is KL0 corresponding to XL being 0, and KL1 corresponding to XL being 1. And there is similarly 2 possibilities on the right side. So there is 4 possibilities of these inputs. Whatever possibility, whatever case I have, so I will have some input, some key on the left and some key on the right. This gate will be some computation, some description will allow me to, given these inputs, compute the key corresponding to the output wire. And which key will that be? It will be the one indexed by the correct bit corresponding to the wire table, to the gate table, and the input bits, XL, XR. The garbled circuit will be just a collection of these garbled gates for every gate in a circuit. And if each garbled gate allow me to compute allowed P1 to evaluate gate by gate from the wire keys that correspond to input wires input wires for this circuit, for this gate, to the wire keys that correspond to output wires on the circuit, then I can compute now locally one by one, right? Each of these gates, because I will have the key corresponding to the correct bit on this wire, and a key corresponding to the correct bit on this wire. And I'll have this garbled gate that allows me to compute the correct key on this wire. If there is such garbled gate representation that allows me locally to perform this computation, then I'll just recurse and I'll perform this locally. Now, given the correct key corresponding to this wire and the correct key corresponding to this wire, I will locally compute correct key corresponding to this wire all the way down to correct keys corresponding to output wires. Now I need a last element. I mean, I need two things still. I need to understand how can I do this garbled gate computation. What is this computation that allows me to go from any input wires keys to correct output wire key? And I need a second final thing, which is how to go from wire keys on the output wires to bits on the output wires. Okay, so let's, I'm sorry, I'm going over time, but we're very close. Okay, so just five more minutes. The garbled circuit is just a set of garbled gates for each gate in a circuit. Okay, so G hat is simply a set of 4 ciphertexts, an encryption. So what is G hat supposed to accomplish? It's supposed to accomplish this computation, right? From any input, any combination of the input wire keys to a correct output wire keys. Okay, we'll do this with 4 ciphertexts. Encrypt under KL0 and KL1. Sorry, KR0. Treat this as a key in encryption. Treat the pair as a key. And the plain text is K of an output wire. This is a problematic notation of the output wire, but okay. Which one? The value of the circuit at inputs 0, 0. How can I fix this? Let me just call it out, and perhaps nothing will happen if it's a few letters instead of a single letter. Out. Okay. So here L, R, and out are indexes to the wires on this gate. Okay. So this is the key corresponding to the out wire. This is an encryption where this is a key, and this is a plain text. It's an encryption that takes 2 keys, and the thing for at first, you just XOR the 2 keys. Okay, so the key that you use to encryption is an XOR of the 2 keys. That doesn't technically work because there's correlation between keys, but just think it's an encryption that you need to have both of the keys to decrypt, and if you have just one of them, you cannot do anything. Okay, it doesn't leak any information about the output. The second ciphertext in this table of 4 ciphertexts is an encryption under a key KL0 KR1 of the value Kout at G01. Okay, so again, this is the key, and this is the plain text. Okay, and well, when we complete this thing, right? So the third one is KL1 KR0. That's the key, and the plain text that you encrypt is Gout, corresponding to sorry. The plain text you encrypt is Kout, and corresponding to this bit. And the fourth one, right, is the encryption under KL1 KR1. And what's the plain text? Kout, indexed by G at 1,1. Okay, so this vector of ciphertext is the garbled gate. Okay, so the garbled gate is a vector of 4 not vector, it has to be a set. Okay, so sorry, it's a set. That actually is important, not obvious why, maybe. Okay, that's the garbled gate. What is the evaluation procedure that, given the proper keys, allow you to decrypt a proper output? Well, the garbled gate is a 4-tuple of ciphertext. I have 2 keys. I don't know whether my keys are what bits they correspond to. Is it a 0-bit key or is it a 1-bit key? I'm not supposed to know. The only ones I do know is the ones that correspond to my input wires, for which I know the bits, but later on I'm supposed to lose this correlation, right? Because as I was arguing, keys by themselves cannot be correlated to which bit they represent, they stand for. And so if that's the case, then I don't know, let's say that they are orders. I don't know which bits I have, which keys corresponding to which bits I have. So I try to decrypt this ciphertext. I see if I succeed. This means that this encryption cannot be any, just CPA secure encryption, right? Where you decrypt and you always succeed in decrypting something. Because then I would decrypt this ciphertext and I would get some value. I would decrypt this ciphertext using my keys, and even if these keys are not matching, I would decrypt some value. And I don't know which of these 4 values is the correct key out value. So let's make it N has to be key committing in a decryption under wrong KLKR pair leads to a reject sign. Okay, so think of this as an authenticated encryption. right? You decrypt using the wrong key, and it actually tells you, no, you didn't decrypt correctly. That's simple to implement. For example, encrypt here not just a key, but a key preceded with a string of 128 zeros. Then most encryption, think of any encryption mode. It's easy to achieve the property that if you decrypt under wrong keys, it's negligible probability the plain text will have the proper string of leading bits, but the correct one will. So then you will know that's the one to take. That's the value of key out of the key on the output wire. Then you should take and recurse this computation for subsequent gates. But this enc, okay, and but also what follows, if only 4 of these ciphertexts decrypt to a non-paired, then they cannot be ordered. G vector of 4 ciphertexts has to be randomly permuted. So during garbling, the garbler cannot simply enumerate these 4 ciphertexts in a canonical order. He has to create them and then permute them. Why? Because an evaluator having some keys, if they were just in a canonical order, and let's say the first ciphertext leads to non-bot, then the evaluator knows that whatever keys the evaluator had correspond to 0, 0 on those 2 wires. So the evaluator would learn the true bits on that wire, right? This is not supposed to happen. Throughout the computation, the evaluator should be kept in the dark of what the real bits are, and the only bits the evaluator would be able to decipher are those corresponding to the output wires. Okay, so this actually we're done. This is the garbled circuit construction. You're simply garbling each gate. Garbled gate is a 4-tuple of ciphertext, and here you see what this 4-tuple is. The final piece is so. Okay. So what do we have? We already have this vector of keys, of garbled keys, and we almost have the garbled circuit. There's one more element in the garbled circuit, and it is a lookup table that allows us to allows the evaluator to go from keys on these output wires to bits on the output wires. That lookup table is the following. It's a set of encryptions under each possible output wire bit, and you know what? Let me just do this here. So this is the garbled gate. Now the circuit, the garbled circuit is a set of garbled gates. So these are the set of garbled gates, and as a lookup table set. So these are, the lookup table is an encryption, is a set of encryptions under the output wire key corresponding to bit B. We will encrypt bit B. And we will do that so here, this is the key used in encryption, and this is the plain text. And we will do that for all W's, all bits, and all W's in the output wire set of circuit C. Okay, so the garbled circuit is all garbled gates, and this thing that can be called a lookup table. From keys on output wires to bits on output wires. On these wires. Yes. So now you have the whole protocol, because what was the protocol? P1, P2 garbled the circuit and created the garbled keys, the set of keys for the wires, and transferred the set of wires corresponding to his inputs and the counterpart inputs either in a straightforward way for his inputs or during OT for the inputs corresponding to P1, and then created the garbled and transferred the garbled circuit. The garbled circuit is a collection of garbled wires for every gate that allow to go from garbled, so from keys corresponding to the input bits for every gate to the keys corresponding to an output bit on that gate. And so the evaluator takes this garbled circuit and the keys corresponding to input bits and evaluates these gates in a garbled way for every gate in the circuit, going from the input to the outputs, from keys to keys, from keys to keys, okay, all the way down. Finally, it has the keys corresponding to the output wires, and now it uses this lookup table. How? It has a key for every output wire. So he goes to this lookup table and tries to decrypt either both of the two entries corresponding to that output wire, and sees which one succeeds. Right? Again, it is a key committing encryption, and gets the output bit. Okay, so this can be implemented in many ways. It's very simple. And that's it. Okay. Did you get lost? Do you remember? If you didn't get lost, or if you got lost at some point, are you able to stay where?
Maybe the differences between the two.
The differences between
between this and the first one. So
GMW?
here we really don't need to send as much information back and forth, right? It's one round only.
It is one. Well, yes, one round, or constant number of rounds, right? It's
yes, there's the OT.
Yeah. And the OT can be piggybacked on this. So P1 can first send the encryption of his choice bits, and P2 can respond and send all this. So this is really two flows, or it could be just two flows. And P1 already has the output at that point, right? So
Right.
if you wanted, this basically has a query, which is first move in OT, and a response, which is garbled circuit, and the response on OTs, and you're done. Like, so if you wanted, privately preserving database query, you will have the same round complexity as in database query. Okay,
Right.
except of course that this takes a bit of bandwidth and computation. One thing about this is that this is purely symmetric computation, symmetric crypto. Right? It's a symmetric encryption that encrypts some keys under other keys. And a lookup table, of course, also. Right? So the only public key crypto is in the OT. But there, and so first of all, the OTs are only done on input wires. So if you have a computation where the inputs are not very long, not very large, but the computation has many gates, then you're already winning because the OT is only happening on input bits. Moreover,
Right.
the
Like the
number of
database
OTs
queue.
really corresponds to the length only of X. This is only done for, so in a database application, if X is a query and Y is a database, then Y could be huge and it would influence the bandwidth of, right? Because Y, the inputs determine the size of the circuit. So if Y is huge, then the circuit that computes on that Y is also huge, presumably. And unless some of the inputs are just not used at all. So this will have high bandwidth, but the OT would be only corresponding to the P1's input size, which is the query, which is supposed to be small. Okay, this was not so in GMW, where I had an OT per every gate in the circuit.
So is there a way of, like, I guess there's no way to make the bandwidth small if the database is big, right? So P2 would kind of.
So, as I said, the game on doing the stuff is still on, and there are surprising stuff. So you look at this thing, and it's sort of obvious. Okay, if you have to send 4 ciphertexts, right? Okay, so like no, you can compact it to like less than 3 ciphertexts, which is very odd, right? It's not clear why. Next, for some gates, common gates, so the most common gate in circuitry is an XOR. You can optimize this so that the XOR gate is for free, which basically you take a random circuit, like 75% of gates or something like this is XORs, and or 50%, right? So basically you reduce the complexity by that factor, and so you can compact. Bandwidth is a bottleneck of this. So even constant factor improvements, create measurable improvements in practice, right? There is a recent result that shows you there is some efficiency issues in that as well, but you can compact the bandwidth so that it is every gate, not only these gates can compact, and you don't have 4, you have less than 3. The gates corresponding to the whole layer of the circuit can be all compounded. So the whole bandwidth is related to the depth and not the size. It is really kind of amazing because this is a very recent result. Nobody, I think, believed that this is possible, and then somebody just did it. Okay. So, this field is full of apparent bottlenecks, and nobody knows how to go over, or nobody even thinks that it's possible, and then somebody does. well, the OT extension in a way is also amazing already because this bottleneck for GMW more pronounced, but here also, if these are two medical databases, the OTs would completely kill you. So the fact that you can compact them is rather striking. And we'll see that next. If you have some questions, fire them. And if not, we can talk next time, and it's a very the construction is it takes time to sink in, and also it's really rich. It has many aspects which are interesting, and many surprising improvements.
So I guess P2 in this case will always process the entire circuit for every party. So he always needs to get, yeah, but I mean, like every time a party makes a query, he needs to get random
yes.
keys.
So that's a huge part. Yes. What happens if you try to reuse the garbled circuit for many inputs? Mm-hmm. And this construction will fail. You cannot reuse the same set of garbled gates. Maybe let's see it next time. Mm-hmm. So what we are still, yes, this is an incredibly nice question. Could you somehow, so first of all, let's see what goes wrong if I try to use the same garbled circuit and I perform these on many, I allow the same garbled circuit to be computed twice on two different vectors of input. One vector corresponding to one set of inputs, and another vector another set of inputs. This construction goes bad. It reveals more than than what you would like from the security perspective, right? Which is that you only reveal the outputs. Okay, so unfortunately, if I reuse the same garbled circuit, I cannot simulate from just the outputs of the circuit on these two input vectors. And in fact, explicitly, I can compute more information about the input vectors than the two outputs are giving me. Okay. When you see what happens wrong, so this is actually a nice exercise. Try to figure this out. Like what would the same circuit, same garbled circuit? What happens when you do it twice? You get two vectors of these wire keys. One vector corresponding to first version of input X, and the other vector for the second version of input X. What goes wrong? So what else can you compute? And you can compute much more than the value of the circuit corresponding to just these two inputs, so X and X prime. Okay, so that's a very nice exercise. And once you see it, the question, an obvious question is, well, okay, can I have some reusable garbling scheme? A garbling scheme that would allow me to reveal keys in such a way that they will only allow computation of a single output, C on a single input, single vector X. Yeah. And of course, another very important consideration is how do you upgrade this to, okay, where were we? We only saw it how to do it for 2 players. And so far we are only honest but curious, right? In fact, what will later, when we get to ORAM, we'll see that the Boolean circuit limitation is the significant limitations. There are other models of computation where you can structure the computation differently. And okay, so you can go over this limit as well. Okay. So there is much more to see here. And yeah, if think of reusing this on many inputs and the same garbled, we're using the same garbled circuits. So what goes wrong? Okay, so see you next time.
Bye.